siblings, friends, fellow Earthlings, and those who each bear one part of the current accumulation of billions of years of time for our existence. Welcome to Ask An Astrobiologist, the show that celebrates the science and the scientists involved in our quest to understand the nature of life. I'm your host, Dr. Graham Lau, also known online as the Cosmobiologist, and of course, we're brought to you by the NASA Astrobiology Program and SegaNet.org. Now, before I introduce our guest for this episode, as always, we want to send a huge shout out and thank you to everyone out there who interacts with our posts about the show, who follows our newsletter to get more information, and those who interact with the polls that we put out on YouTube running up to every episode. This month, we're going to give a special shout out to @TheRenderingReality and @Ananya Agrawal on YouTube for commenting on our poll with some very thoughtful ideas regarding a poll that I'll share a little bit later in this episode. Now, I am super excited for today. We have a guest coming back who was last on our show 6 years ago. Dr. Sara Walker is a theoretical physicist and an astrobiologist. Her research interests cover things like the origins of life, the physics of life, emergence, complex systems, and honestly, far more. She's a professor at the School of Earth and Space Exploration at ASU, and she's the deputy director of the Beyond Center. And I should also mention that she was one of the original co-founders of SegaNet.org. Now, like I said, Sara was last on the show in 2018, 6 years ago, so a lot has changed, but I am so very excited now to welcome Dr. Sara Walker back to Ask an Astrobiologist. Sara, welcome, and thank you for joining us.
I am thrilled to be back. It's been a long time.
It has, yeah. But so we were talking just before the show, and I mentioned the last time you were on the show, you also had a whiteboard and some books behind you, and that's pretty awesome and pretty fitting, I think, for your career.
Cool. Yeah. A different office, but same vibe.
Yeah, there you go. Going back to the episode 6 years ago, you shared with us about your origins. You mentioned how your father was a hairstylist. Your mom was involved in antiques. And your family cultivated this art in your childhood, but that science kind of became your creative outlet. I wonder, in your life and in the last 6 years, how science has evolved as your creative outlet.
I think what I really love about it is the capacity for using your imagination to create new things. Artistic expressions are supposed to be about seeing features of the world and like looking at them through fresh eyes, or at least this is sort of a lot of the, what artistic artists do. Like they make us see the world differently. And I think science also makes us see the world differently if we're willing to look at it with sort of unbiased filters from like our previous training and stuff. And so a lot of what I do is basically trying to break down the way that we think about things to sort of like basic parts, and then try to think through what would they look like if we reconstructed them for the kind of problems that we're facing now, or the things that we're asking. And I think this is really critically important with the questions of astrobiology, because the questions we ask are so hard, and it's very clear that we need new tools to answer some of them. And it's really hard to come up with those kind of ideas unless you're willing to change your own conceptions about how you think about the problem. So that's sort of my favorite mental exercise.
I love that so much. The idea of like throwing away your pet theory and thinking about what else is possible. It's a very healthy act in science.
Yeah, it's an existential crisis.
Absolutely. I just gave my very first TEDx talk, and part of it was about how like we have these existential crises, but that astrobiology is its own kind of thing for us. Also thinking about our place in the universe. Now you've had quite a journey getting to where you are now. You started off in community college, went to undergrad, and then kind of you discovered theoretical physics. So if someone asked you to like define what your career is, how would you describe that?
I am a deeply curious person, and I also am really motivated to understand things and how things work. And so I guess what happened for me is I'm not one of those like scientists that was like, I've been looking at the stars since I was like 2 years old. It's just not me. Like I didn't really think about science much as a child. And what happened was I thought going to college was a good idea, but my parents hadn't been, and I didn't have any examples from my family. So I went to our local community college, but I knew I liked science. And so I just took science and math. And I really fell in love with the thought process of science, in particular, what physicists do well, which is one of the reasons I decided to become a physicist, which is to come up with abstract descriptions of nature and the fact that our minds are actually capable of describing reality at a deep level and coming to new kinds of understanding. And that kind of understanding doesn't just allow us to understand the world, it actually allows us to kind of in some ways shape the world, right? So the future of the history of like human evolution has been shaped by the kind of ideas and technologies that we built. And so I really think that process is deeply human. I don't know, and at least as it exists now, and it could be, like other kinds of entities have a similar process. But for me, that became a huge motivator because I think that there is so much more that we don't understand and could understand. And what I started to see in my career is there were a lot of assumptions about understanding things that were very clear to me that we didn't understand. And so I think that sometimes we, because we're taught knowledge from previous generations, there's a lack of capacity to challenge that and like really try to say, well, are these ideas still the best ideas we have, or could we come up with better ones? And so that exercise as a scientist to me is incredibly enriching. So, I never really want to work on an idea that's accepted. I always want to work on one that's like something new and something different and might change some of the ways we think. But I think working in that space, there are ways of doing it constructively where you can see where the logic pieces put together, but you might have a better explanation by talking about it this way than you would if you talked about it this way, which we can get into some of what that looks like in practice. But I guess that's part of the thought process.
Yeah. I love that so much. And our species, you mentioned, we've come so far. It's maybe 200, 300,000 years or so since our species first emerged, and in that long window of time, all of our technologies, tens of thousands, maybe 10,000 years old. And then, all the current science that we're doing is really only a few hundred years old. And even that's changed a lot over that time. And so we'll certainly talk a lot about time and lineage and things like these. But how do you see your role as a scientist and part of this kind of progress of humanity?
So I think one of the things that's critically important is to understand that like anytime we're alive, we're living a moment in history, right? So I think about that a lot with the science that I do. And actually I do this as a cognitive exercise. I think about the questions that are being asked now and what questions I think are important. And I think about the history of science and how we had these major conceptual shifts and what was happening in that cultural moment and also among the scientists that were working in that time and how those things intersected. And for me, this is actually a really important exercise because I think it's really easy to get stuck in now and what like seems important in this particular moment, and particularly for early career scientists, is like, I got to get my PhD, so I just got to do a problem I can do in 4 years, and we all kind of think about it on these really short horizons. But I think if you kind of take this broader view and you really are, have the opportunity to ask and you want to ask these deeper questions, like you really have to think about what kind of changes are necessary to mediate answering those kind of questions. And so I really approach a lot of my philosophy about the science and the science itself from thinking about the nature of conceptual shifts and how we might mediate them and how they've happened in the past and what that might look like if it was happening now. And I think part of that is really motivated by this perspective that science is just beginning. It's not ending, right? So as you pointed out, we've only been doing science for a few hundred years. To think that we've actually achieved an understanding of everything fundamental to me is like radically premature. And so when people talk about these final theories, it blows my mind that that's even a cultural thing that we talk about. Like I just don't even understand how that could be a thing. So I'm really interested in developing sort of the next generation of theories that help us dig a little bit deeper and understand things at a more fundamental level, but also have the understanding that they'll be replaced at someday by some other kind of understanding that we can't even anticipate living now. So I think that temporality of the scientific process and really understanding where we are, what we can do with our current technology and ideas, and where we can go with them is super important. And also realizing that any piece of knowledge that you learn from a scientific textbook was somebody going through that process. I'm actually reading this crazy book right now called Inventing Temperature, and it's insane because we just take temperature for granted. And the whole process of coming up with temperature as a measurement is like, it's totally crazy. Crazy. Anyway, sorry. That was
Yeah.
I'm like very excited about that book right now.
The transfer of heat, it's so crazy to think about, like the fact that like we understand that some objects have certain energy, and energy is transmitted from one thing to another. And like the very thought of temperature, I remember even as an undergrad being like, whoa, really? Like it's not just like a thermometer measurement of some physical actual thing that's like stagnant. It's a change. It's a change in space and time.
Right.
Pretty groovy.
And the coordination of it's really like something like the fixed point of, like that water boils at a specific temperature. Like before you could measure that, how do you measure that? Because you can't say it boils at the same temperature unless you have a reliable measuring device. And so like these sort of, paradoxes are really hard and really deep. And we just take for it granted now that thermometers work. And like there's a thing called temperature that's a real objective feature of the world without realizing all of the intellectual work that went into that by many minds over many generations. So I think that's very important for us to know as astrobiologists, because we're inventing new areas of science, and we have to be really cognizant of the fact that process is hard. It's multi-generational. It's very, it's many minds working together, and there's often a lot of conflict about ideas, and that's totally normal and natural in the history of science, and actually productive that people don't agree. And it's just a whole ecosystem of things that I think, reading the history and philosophy of science is actually critically important for understanding what we do.
Yeah. Absolutely. It's a great segue for me to share the poll that we put out and leading to our episode. Now, we always like to poll our audience in something kind of relevant to what our guest is researching, but also kind of maybe a little bit out there. But in prepping for this episode, we were in conversation talking about the idea of astrobiology being pre-paradigmatic. I think that came from Lee Cronin originally. But the idea of like paradigms in science, and you're right, like science isn't always consensus. Sometimes there's another viewpoint that can come out, and it might actually change how we do science. And so we asked our audience for what they thought like the major revolutions in science were. We gave a few possible answers, including the germ theory of disease, Newton's laws of physics, Copernicus's sun-centered universe or sun-centered solar system, Einstein's theory of relativity, or we offered the option for others as well. Of the options we gave, germ theory of disease was the one that people selected as the most impactful for human civilization, but a bunch of people jumped into the comments and suggested that the most impactful was evolution and Darwin's theory of natural selection, which was one of the very first big understandings of how evolution can function or might function. I wonder what your view is on that. What do you think has been the most impactful revolution in science so far?
I think the idea of measurement, actually, like I'm very obsessed with measurement right now, but I think it's easy to have ideas. It's hard to anchor them in the physical world. And so if you look at a lot of the early progress, like I think people will say the paradigm shift of like the generation of Galileo and Newton was the theories that we came up with about the nature of gravitation and things like that. And I think that's absolutely true. But I think the sort of unsung heroes in that story were the technology that existed at that time that enabled them to do that science. And so like clocks were invented with like second precision, only shortly before Tycho Brahe, he took his measurements. And, the ability to measure precisely the timing of balls rolling down inclined planes and planetary motions was critical to the development of Newton's theories. So, and I also mentioned this thing about temperature, which is, like thermodynamics couldn't become the science it was until we had reliable devices for measuring temperature. And this is actually one of the things that we think about quite a lot with developing a theory for life, is this very tight coupling between measurement and the theory, and having the abstractions actually embedded in structures in the physical world that are not just our imagined conceptions of it. So I think, one of the biggest paradigm shifts in science has been the idea of measurement and what measurement enables. And actually, it's super interesting to me right now, because in the current moment, with all of the emphasis on machine learning, there's a sort of emphasis on this idea that if we collect enough data, machine learning algorithms can do the science for us, but they don't know how to invent new measurements. And if you look at the major, even when you talk about sequencing the human genome, it was because we had new devices like PCR and things that allowed us to actually, enable sequencing genomes. So I think you can't decouple science from that historical context and the technologies and what's, all of these features. So I think that one for me, I don't know, it's maybe not what you were looking for, but I'm just obsessed with measurement right now and what it means, because it's very non-trivial.
Yeah, I love that so much. And like, we've created new ways to enhance our perception of the universe. And a lot of that is measurement. We've created new tools to measure things. So without a microscope, the germ theory of disease wouldn't make any sense. We could never see things that small to really understand where it's all coming from. And so even though we had Louis Pasteur and his swan neck flask experiments, without really developing microscopes and the capability of seeing microbes and then developing the tools to understand DNA and measure genes, we wouldn't really know how these pathogens are actually impacting us. And so I love that so much. I'm going to jump ahead in my notes just a quick minute, because I had this quote in here that I love from Frank Herbert in his book, Dune Messiah. He says, "There are many degrees of sight and many degrees of blindness. What sense do we lack that we cannot see another world all around us?" Do you think that given human perception, how we've evolved to sense the universe, and also our current tools for sensing even more than we could biologically, do you think there's still something that we might be missing out on that's really crucial for making the next generation of measurements?
Um, just in science in general, I think it's deeply interesting that intuition is undersold, especially in the frontiers. So, if you go into an undergrad education in science, you're taught there is an objective reality and it's independent of humans, and we go out and discover it. But if you actually look at the history of science, like, I'm not denying objective reality, by the way. I just want to be very clear on that. Like, I am a physicist and think there's a material world out there. But like, the ways that we come up with new knowledge are often at least the ones I get most excited about are people that really changed, like, they challenged what they had been taught about how the world worked. And they challenged it in ways because they were trying to put together pieces that just couldn't fit together. So I do this a lot as an intellectual exercise. Like, I work across a lot of different disciplines, because if you're in one particular discipline, things may seem coherent and like, everything's working. But if you try to add another piece to that, that's just, outside of what people in that field have thought about, and you try to make it fit with the other ones, you start to see all these holes and these patches where these things don't fit together. And those are really opportunities for progress. And so the way that I approach those kind of things are, one, to look for those kind of things, and then also to try to find some sort of guiding structure about how to connect those things. And that's a very actually deeply intuitive and very abstract process. And I think what we're missing in a lot of the ways that we talk about science is actually how much, on these frontier questions, it's much more like an art than the thing that we're taught objectively as undergrads. And I forgot this quote by Einstein, but I had it in my book, which is about how, knowledge can get you from A to B and imagination encircles the world. And he was deeply intuitive in the way that, he constructed the theory of relativity. I keep saying this in interviews, and I keep meaning to look up and find this quote. So if anybody out there can find this quote, that'd be amazing, because I haven't found it yet. But someone told me that he once said he could feel a light beam in his belly, right? Like he kind of embodied the physics he was describing. And I think that sometimes we decouple ourselves so much from the problems we're trying to solve because we're trying to be a bit objective about it. We forget that the systems we're studying are actually ourselves. And I think that's critically important in astrobiology in particular, because we don't know what life is, and we don't know when we're constructing scientific experiments, when we're putting this thing called life in, because we're living things and we're observers in the universe and we're controlling the boundary conditions. So I think kind of placing yourself in the equation and actually following, like really thinking about not just science as objective, but I'm a human doing science. Like, what are the questions? How do I feel about the questions? What are the things that interest me about them? And I think a lot of the real pioneers in science followed things they were deeply passionate about, and really had some intuition that like didn't sync up with like the dogma of their time.
Yeah, absolutely. Yeah. I want to come back to intuition in a little bit, talking about artificial intelligence. But first, you did mention that the quote you mentioned from Einstein is in your book. And so I should mention you have a new book out, Life as No One Knows It, The Physics of Life's Emergence, a fantastic read. And if I can, so on the concept of questions, the questions we ask, in the book, you wrote, to get to an answer for what is life, we may need to ask a different question, why life? And you kind of talk a little bit in the book about reframing questions. And I wonder, like, for astrobiology and this vision of like, what is life, which we've been asking for a long time in astrobiology, why do you feel it's important for us to kind of reframe that question?
So one of my perspectives on doing science is like when I look at the literature, if people have been asking the same question for decades and not getting an answer, like they'll get answers to sub questions within a space, but not the ultimate question that motivated that space being created in the first place. That suggests to me that that's not the right way of asking the question. And the example I usually like to give, and like I'm a huge fan of prebiotic chemistry and periodic chemistry experiments, but I think that prebiotic chemistry is a different science than, for me, what the origin of life is, which is the transition from non-living to living matter. And, most of the original life literature for the last, 60 years or so has been dominated by organic chemistry and trying to synthesize under prebiotic conditions. I will say, quote unquote, prebiotic conditions, molecules that we find in living things. And I actually think that that is not at all the right paradigm for asking the question about the origin of life. And I think it's very clear from 60 years of experiments that that's not the right paradigm, because we haven't gotten any closer to addressing the actual question of the transition from non-living to living matter. And I think part of the problem is some of those experiments are actually over-engineered in the sense that we are putting too much selection from us understanding the endpoint of the experiment into the experiment and engineering the conditions. So it might be that each feature, like the particular pH or, the UV radiation or whatever it is, might be something that was present on early Earth. But the boundary conditions of purified reagents and doing things in a round bottom flask and having those precision controls that experimentalists have over those things are absolutely not prebiotic. You're basically replacing a biological cell synthesizing those things with a technological entity, but they're nonetheless biological. So, the real challenge with origins of life is how do we remove all of that informational infrastructure and all the things that we impose as evolved entities that exist in the universe, and do an experiment that has none of those things and ask the question of how do we get life out of that thing? But that's really hard. So then the question is, how could I ask tractable questions in that space if I really recognize that this is what we've been doing and this is the way we need to go? And the challenge there is like there's a whole body of knowledge there that could be capitalized for like asking the more general question, and the transition becomes how do we move that knowledge over? And that's one question I've been thinking about quite a lot, because I think there's like ways of curating data from prebiotic synthesis that actually could account for bookmarking human agency in the experiments and things. But that's a long project also in a separate conversation probably. But it's one example where I think this idea of like, are you asking the actual question? Are you asking the question the right way? Could you reframe the question? And what is life and why life are also in that similar vein. Like we've been trying to define life for ages, and you might get some descriptors of life, like life is a self-reproducing chemical system capable of Darwinian evolution, which is one many people in the astrobiology field will know. Or, life is something that metabolizes, life is a compartment, life structure. Like there's all these kinds of definitions, and they kind of box you in prematurely, I think, and impose constraints that are not indicative necessarily of the universal thing that we want to call life. And maybe we don't know what the universal thing is we want to call life. And we should not assume that we know what that thing is. And so reframing the question becomes more about what is it that life is doing that we want to explain? And that's the sort of why life question. And I think the thing that I've landed on with my collaborators is that life seems to be the only thing in the universe that can generate complex structures, things like us, things like microphones or Ask An Astrobiologist or, DNA. Like these are not things that you see spontaneously forming in the universe. They seem to be products of evolution and selection and information processing systems. And so if you ask questions about what physics could explain that, you get to a deeper level of description, and you're not actually biasing yourself on a preconceived notion of what life is. You're allowing life to be the answer to your question instead of trying to come up with an answer for life. And I think that's a better way of framing it.
Yeah, I love that. And so in your book too, like you talk about, these hard questions in science that have been around for a long time, like what is matter, what is life, what is mind, like questions like, are we conscious? Is anything else out there conscious, having these experiences? There's really big questions, but I love too that you kind of explain that, there's a way to approach maybe trying to figure out physical laws that include those doing the physics, that include us in the equations. Do you think there's a reason that we haven't included us in the equations for so long in the history and philosophy of science? Do we have a drive, maybe because we want to be objective, that we've just chosen to try to remove ourselves as much as possible?
I think that's absolutely true. And so science is built on a notion of objectivity. I also think, that again, it goes back to thinking about like the people that invented modern science, like what was their conception of nature and how the universe worked. And, at the time of Newton and Galileo, there obviously like Galileo got into trouble with this, but like the church was very important. And there was a lot of ideology about the universe being very mechanistic and driven by potentially an intelligent entity that designed the universe in some capacity. And I think even if you didn't share the religious beliefs at that time, that was just sort of a cultural way that people thought about the way the world worked. It seemed to have some regularities of it. Like they were things that were not understood by humans. It wasn't clear they could be understood by humans. And so this idea of appealing to what became the structure of physics, of some law that set the universe in motion and actually describes the universe, what we call the laws of physics, and some initial state that got it all started, seemed to be very explanatory of people living in that time's perception of how reality should be described. At least that's my perception of it. Like I could probably read more about like the original literature from that time period, but I think these kind of thought experiments about what were they thinking and how much have we become culturally ingrained because of the way that people conceive nature in the time that they lived is super important. And I think what's happening now, which is super interesting time to be alive, you'll see a lot of work across a variety of disciplines, from like people in art to philosophy to technology to, fundamental physics, kind of pushing against this idea and really trying to think more about the observer inside the universe, and also that the universe, like maybe questions about what's outside the universe are not so meaningful. And we can't know everything, but we live, we live in a observational horizon defined by our technology and our biology. And some of the sort of, things that emerge there that I think are really interesting is we see the world changing around us and we see our agency changing the world. So it's not like in, thousands of years ago when the climate changed and humans had no control over it, no agency, no understanding of what was driving those changes. Now we understand climate and we understand that we have some agency in the way climate behaves, right? And we understand that technologies that existed 30 years ago are radically different than technology. Like you literally see evolution happening around us and you see the impact of life restructuring the physical world around us. Like literally everything in this room that I'm sitting in right now is the product of a human mind. And so I think if you think about the long arc of human evolution and human history, it's not surprising that it took us as long as to now to really see that maybe this idea that there's fixed regularities that exist autonomous to us, and like we can use them to describe the world is not exactly the best description of us as living agents evolved from the structure like inside the universe that actually are part of the structure of the universe itself, doing something. And the place you see this in sort of like the popular science is like we're the way the universe comprehends itself. But, I think the actual deeper story is we're literally how the universe constructs itself. It's not just we're sitting here as passerbys understanding things, like we're actively changing them. And I think that's very deep in the physics of life, and it demands new explanations. But it's also not surprising to me we don't have those yet, because I don't think we had enough history to recognize that that's what was happening. Like you have to see these patterns over time, and they have to be passed from generation to generation to build a narrative about what's happening, which our species is very good at. And you have to build technologies to test, the things that are actually like really out there versus not. But I'm very interested in conceptual shifts in science that are happening now, which move from this idea of objective outside observers to understanding there might be an objective world, but the subjectivity of us as observers inside of it matters to how we structure our theories and ideas about how it works.
Yeah. Yeah, and there's so much like it's weird. We those of us at least who are a little bit older have experienced enough change through time to say like, oh yeah, everything changes, but then we imagine ourselves in a place that's static and our future as what it is now. It's weird how we humans kind of process that way. And as you were speaking, something just came up in my mind that I forgot to tell you about. You once tweeted many years ago this really awesome phrase that I have now reshared so many times, and I don't think I've ever actually reached out to tell you that I keep resharing it. I even forget when the tweet was, but some years ago, you wrote that that mathematics is not the language of the universe; it's the language with which we understand the universe. And I love that so much. It's kind of in that same conception. Then it's this idea that like we've heard for so much time that like mathematics is the language of the universe. When you think about like Contact from Carl Sagan and other movies, and like we're like, oh yeah, of course we're going to talk to aliens using mathematics. But then the question is like we have a certain mathematics based on who and what we are that helps us understand the universe, and maybe aliens will be different, right?
Yeah, no, mathematics is one of my favorite thought experiments because I think it's a deeply challenging one. Because again, it comes to like what's been culturally ingrained in us, and sometimes these are like 1,000-year-old things that we've been telling ourselves. So, if you go back to the Greeks and like the way they talked about mathematics as being this perfect world of forms, it's, like it has a sort of otherworldliness, like it's objective and exists autonomous to humans. But there's all kinds of research being done now about how we have come to learn mathematics and invent new kinds of mathematics. And even yesterday, actually, in my class here at ASU, which is a class on what reality is, we were talking about math. And, it came up in the discussion that, like there might be some boundary in mathematics where you really could say it was an evolved system because, the abstractions become so decoupled from like the anchors that we have in the physical world. Like counting, you might say, is like universal objects really exist. You can count them, but not every brain is going to evolve to recognize number. Some might evolve to recognize area. And actually, in fact, studies of early neuroscience development of humans are suggesting that our brains are pre-patterned to really be able to count, but we don't recognize area very easily, and other species might recognize area better. So you can think about, if you think again about the historical contingency and us as part of an evolving structure, you can see that these sort of early things that happen in our evolutionary history really shape where we are now and how we think about things. And I think mathematics is absolutely that. And so I don't believe like what we talk about with mathematics is a final language or an absolute language or an objective thing that exists autonomous to us. Although I do think it's interesting that it maps regularities that we can talk about in a well-structured language to features that seem objective in the external world. But I think there's languages that will be beyond mathematics. And I like if you look at Gödel's theorem and like the incompleteness theorem and like when math talks about itself, which is what it was about. So like the liar's paradox, the statement is false. It's neither true nor false, right? When you have mathematical statements like that, you see math has inconsistencies when it tries to talk about itself, which I think suggests that there's some other level of description that we have yet to discover that's beyond mathematics. I don't know what that is. People always ask me when I say that, what is that structure? And I'm just like, I can just see it's there, but I don't know what it is. But it's like very suggestive to me in many places it exists. And I think maybe AI, it's beyond. But I think it's good for us to think about the things that it's not just that we should think about where previous generations were and what they thought and where we are now, but what things could be accessible to future generations that we're just not ready to think about yet. And I think just seeding those ideas is an incredibly creative process for, those that will live in subsequent generations to those of us thinking now, because it's almost like these are the things that we weren't even ready to ask. Like maybe you're ready to ask them. And I think there's lots of those things. And I think we don't do a good job articulating that. We always think the problems are solved or we can solve them today. We don't do long-term planning of how we think about knowledge and its progression.
Yeah. Yeah, and that's so coming back then to this concept of intuition and kind of like the next iteration, the next level, the beyond level of mathematics and physics and our thought processes or what it means to be human. You mentioned Gödel. I just recently in my life finally read Douglas Hofstadter's Gödel, Escher, and Bach book, GEB. And I love in that book that he discusses artificial intelligence and he says, AI could just as easily mean artificial intuition or artificial imagery. Now we have LLMs and generative AI. Of course, it can mean artificial imagery. We've seen that. We've seen it creating artificial language constructs based on what we've developed as humans. But this makes me think about his concept that it could be artificial intuition. Do you think maybe that next level of determining mathematics or physics, these next levels are going to require either us working in tandem with artificial intuition, or do you even think artificial intuition is going to be possible in our near future?
Yeah, I have so much to say on this. I think a lot about these problems. Yeah, it's funny about Douglas Hofstadter. So like I think like GEB is really hard for people to get into. So I just want to note for people out there that if you ask Douglas Hofstadter himself, he would say I Am a Strange Loop is his favorite book and actually covers what he wanted to say better than GEB does. And he actually would prefer people talk about that book rather than it. Like, it's super interesting because like GEB has been such a like, like beyond blockbuster success as a book, especially for something so intellectually deep. And I think it's an artistic mastery, but it's just very funny. His conception of like his own storytelling is very different than the way we talk about it. I think that's a fascinating fact of human social dynamics. So, but on the question of artificial intuition, there's this whole debate about whether artificial intelligence is creative or not, or could be creative or not. And I think for me, intuition is really underlying creativity, and it's deeply tied to the question of novelty. And so, this is something that I think current physics doesn't afford very well. And in fact, we don't really know how to talk about in science, is whether the universe creates genuine novelty. And in some sense, I think novelty is something that couldn't be predicted from the past. And so I have a very different conception also, I should say, of the past than most people do. Like, most people think the past is in the past and it's gone. And I think the past exists rolled up in the present. And it's a very physical feature of like, and it gets into the physics of life and all kinds of things I think about with the work that we're doing on assembly theory, but that's a whole another conversation. But what's interesting about artificial intelligence is, they require data to be trained, right? And they become predictive algorithms. But what you're really predicting is, in some sense, patterns that have existed in the past, right? Like if there's something genuinely new in the future, an AI is not going to be any better at predicting that than we are. And this notion that we're creative is actually somehow that we can construct things that we didn't anticipate could exist, centuries ago. And there's plenty of examples of that. I can't imagine that. I don't know. I'm trying to pick something in my environment that someone several hundred years ago would never anticipate. A box of crayons. Here you go. I don't like, how predictable is this object from the prebiotic chemistry of early Earth? But this is what life does. Life evolves, life learns, life constructs, and that space of construction actually enables new things to exist. And I think artificial intelligence is deeply interesting as kind of a layered architecture of information processing in our biosphere. But I don't think that, and I think integrated with humans, to answer your question, I think is deeply creative. But I don't think about it as this like separate other intelligence that's, very different than humans and, somehow will usurp us. And I think that's actually Douglas Hofstadter's fear. He thinks AI is really AI. And I think it's part of an evolutionary progression of architectures that have been built on our planet. And just like most evolutionary architectures, it will get integrated into this structure of what life is, which is information structuring matter across space and time. And it will continue that lineage of propagation in the future. And whether it individually is capable of intuition and creativity, I don't think is evident in our current algorithms. And fundamentally, I guess the simplest way I could explain where I see that dichotomy goes between this idea of, do we predict the future or do we actually physically make the future? And AI predicts things. And if you give it enough history, it can predict a lot of the past. And since the future looks like the past, it can predict some of the future. But we are part of a physical system that is actually actively constructing itself. And there's no artificial intelligence algorithm that touches that yet, as far as I understand it.
Yeah, I love that you threw in the yet, because you never know. Like, Android robotics in the future, maybe we'll have a system that will change things. But so I have to be true to the time here for my audience.
Yeah.
I could speak with you like every single thing you said so far for like an hour, each different topic you brought up, and there's so much to explore. I want to come back to the idea that you shared that the past is rolled up in the present. You said on a recent podcast I was listening to that it's crazy that there's billions of years inside of each of us. And I kind of want to explore then, just for our audience, the concept of assembly theory. In a brief amount of time that we have, I remember it being called assembly complexity index or pathway assembly index. Now it's assembly theory. But I wonder, so for our audience, could you give us kind of like a 10-year-old kind of vision of how you would explain this very generally to any audience?
Yeah. So I think there's a few points that are critically important, and they're deeply related. So one of them is it possible to measure life? And assembly theory definitively says yes, and that there is a unique signature of what life does or is. And actually, in some sense, this goes back to what we were talking about before, because once you figure out how to ask the question, what would life be the answer to? The explanations you get for what life is might look really different than if you were just trying to define life. So when I say life here, like, is it possible to measure life? I mean something very specific about what assembly theory would say life is, which is the mechanism that the universe builds complexity. And it has to do it along these historically contingent pathways or lineages where you remember some of the past to construct the future. And assembly theory has very rigorous ways of talking about the structure of a physics that would look like that. And also, how would you measure, if you went in the lab, a molecule was a product of such a constructive process that we would call life. And we conjecture that there's actually a hard boundary. If you look at this assembly index, is a minimal number of steps where you reuse parts to build an object like a molecule. Or if you like Lego, like if you want to build a Lego castle, there's like a shortest path to get there if you started from all the pieces of the castle. There's actually, if you order all the things the universe could generate, all possible molecules, by this minimum number of steps, the number of possibilities in that space grows exponentially large very fast. And all that means is the universe cannot generate every molecule in infinite, like even in infinite time, because you could potentially make infinite molecules. So I think it's not possible for the universe to generate every physical structure. Very important point. Like, we can imagine more things than can exist. And so what we see with the structure of this theory is there's a boundary above which, if you observe that structure, that molecule or that Lego castle in abundance, it suggests that there had to be some evolutionary process behind it. And evolution here is a very broad, it's not Darwinian evolution. It's deeper concept than that. It's much more about selection as a fundamental mechanism the universe has for creating structure. And that when you get to these systems that are combinatorially large, like what the periodic table of the elements can generate on planets, the only way to start building structure into that space is to have the thing that we call life. And so that's actually the premise of the theory. It stems from this idea of going in the lab and measuring. So when you're talking about assembly complexity, the reason that was sort of the first way we talked about it, because the question there was, and this was in Lee Cronin's lab that this was developed, because Lee was really trying to make a robot that could make the origin of life. So, like, throw out all the sort of boundary conditions we want to put in as chemists. If I just have a robot that can explore chemistry randomly, how would I know that a living thing emerged out of that? And I want to go in the lab and I want to take a measurement. So Lee was like, banging his head against this. He's like, he's a really amazing chemist, because like the theory is actually him doing experiments. Like, he builds theories by doing experiments. And so he's thinking about a mass spectrometer as a thought experiment, and came up with this idea of measuring assembly index by this recursive use of parts, because when you use a mass spec and you break out part of molecule, you actually kind of do this process in reverse. So the theory started with the idea, go in the lab, measure its life or not. And then, because we have this particular way of measuring this measure, we could build out into all these other kinds of ideas about the nature of life and how we can predict the dynamics and how we can understand when the origin of life happens in terms of this complexity threshold. And there's a whole number of other ways of testing this paradigm about explaining life as the mechanism that the universe generates complexity. And then the other thing I want to say about it for people, which I find deeply interesting, is just sort of the philosophy that emerges out of it. And I had this wonderful conversation with this historian, Thomas Moynihan, who's writing a book actually on historical contingency. I don't know exactly the topic of the book, but I'm really excited about what his project is. But he was really excited about assembly theory, because he's like, for most of human history, we've been missing the fact that, like, history is physically real. Like, we ignore the past as being like gone. And so there have been a lot of it goes back to my point earlier. Like, I think we've lived enough now to know that like that lived history actually is embodied in the present and that we are shaping the future. And assembly theory is a way of formalizing that intuition that we have about even ourselves animating our environment and seeing the changes. So it's operating across a lot of levels, which I think is one of the reasons that it's quite hard to really understand what we're doing. But I think a lot about like the foundations of like when quantum mechanics was invented and stuff and how many pieces you have to put together. And so I think the thing that's exciting is that like we're really trying to build a theory from scratch that explains life and might give really different intuitions and ideas about the nature of what we're looking for when we say we're looking for life. But it's a theory that's tied to experiments, and we can go test it in the lab. Like we are actively planning a research program, and we're really trying to actually start a program to do this, like a big initiative to do these experiments to look for alien life in the lab. And I think if we can realize the origin of life in an experiment, then you prove the physics. And then, you know, for those of us wanting to go to Enceladus or Titan or other places to look for life, like we might know what we're looking for, which would be cool. And we might be able to predict it, but who knows if it'll work. But I think a lot of the early signs and connections that we're making are really exciting. So that was not a short answer, but I tried. I'm sorry.
That's great. No, I love excited. It so much. I do have to jump. Like I could just talk for hours, but I do have to jump to our next segment, the Faster Than Light segment, the series of questions we ask everyone who comes on the show, because I've been told that we have a lot of guest questions, audience questions coming in for you as well. So let's just jump into it, because there's lots of cool things that we can consider when it comes to life on Earth, possibilities for life out there. And so the first question: what is your favorite thing that life on Earth does?
Invents.
Very cool. Yeah, I mean, invention is pretty awesome. Creativity. And next one came out, some of the recent research going on with like AI talking to whales. If you could communicate with any non-human organism on Earth, what would it be and what would you want to talk about?
Octopus.
Okay. Why octopus?
Because their nervous system evolved independently of our lineage, and because it was pre-patterned by the same conditions. And so it's probably the deepest we can go with seeing a neural architecture that's different than ours. And I guess I would want to ask it what it thinks about the external world.
Very cool. I also just saw that an article just came out where a team of scientists have been watching an octopus, or these octopuses that go hunting with schools of fish, and they and the fish like pair up together, and there's some kind of like communication going on there. There's some like overarching system that's causing them to work together to go hunting. And there's also like situations where the octopus will punch a fish if it's not part of the group appropriately, which is really interesting.
Yeah, I love it. They're really cool. I was very influenced by Other Minds. The book by Peter Godfrey Smith is just like really excellent exposition on them kind of being aliens on Earth. Not really alien. Okay. Astrobiologists would know the difference. Some people will call them alien, but like alien means something specific. But they're very different.
They seem bizarre. Exactly. So on that case of bizarre things and thinking about things like science fiction, for instance, has been a big influence for me and many others. And there's lots of great stories we've told ourselves through time about what it means to be human and our place in the universe. But what stories have inspired you to want to explore more about life in the universe? Many stories. I really love science fiction, and I have a lot of friends that write science fiction, but I've been like actively seeking them out. So when I have science workshops, I invite science fiction writers because I think co-imagining is super important. But one of my favorite stories is the story that inspired the movie Arrival, which most people maybe here will be familiar with. But the story itself is called The Story of Your Life, which is by Ted Chiang. And Ted is an amazingly deep thinker. And I actually had the opportunity to talk with him about that story and his inspiration for it. And it's really interesting because a lot of the inspiration had nothing to do with the actual like elements of the story as far as being about aliens and things. It was much more starting from like an emotion and things that we feel about grief. But the story itself, I think, is exceptionally written. So it's a narrative about first contact, but it also plays fundamentally with our concepts of time and how we understand reality, and then also how we communicate that through language.
And I think all of those elements to me are like very deeply tied to the actual existential questions we have and the kind of theories we might come up with when we make first contact. And in particular, like I love that a lot of it was about perceptions of time, even though I think both theories of time in that are not actually the time relevant to aliens. It would be much more like a causal time to give an aside. But anyway, that's a fantastic story. I really recommend it to people interested in being inspired about ways that we could think a little bit differently about first contact and what kind of science needs to go into it. Cause it's also not like the typical, like, I'm a chemist, like going to measure something on a moon. It's like, who's called in is the linguist. Right. So I think it's just got a lot of really nice elements. So I guess that's my shout out for that.
Yeah, it's a very short story to have made an entire movie out of, but yeah, there is a lot of idea there, and it comes in a collection of other short stories that Ted wrote. That I love that entire collection. They're great ideas about language and math and intelligence inside of those short stories.
All his stories are great, so yeah, definitely, yeah.
All right, next question. If you could go back and visit yourself at the start of your career, what advice would you give yourself?
I think I actually wouldn't want to do that because I wouldn't want to intervene. And also, I don't like retrocausal loops. They feel weird to me intellectually. So like these thought experiments always kind of drive me mad because I'm like, you're like literally rewriting how the universe like decided to execute itself. But okay. But if I'm going to play along, sorry. I think part of my answer is like very honest. I would not want to intervene. But I think if I did go back, I would just try not to intervene, like just do what you like. And this includes all the mistakes, right? Like, so I have a lot of things in my personal life that like maybe some people think I should regret. Or like in my professional life, like I should have done this thing and not this thing, or I could have studied harder or whatever else it was. But I can see actively how every single decision I made and even the things that were really challenging shaped who I am today. And I don't think I would change it because I think I'm actually happy with where I am. And I also understand that anything that I don't like about where I am, I can actively work on and make into what I want it to be. And I think that's a moving target. Like who you are is not, like you're talking about static in time. Like we think of ourselves, like we are not static entities. We are constantly changing and we are like, and so like, yeah, I wouldn't do it.
Awesome. So one more question, and this is the favorite, I think, of everyone. What is an unbelievable science fact that still blows your mind?
The speed of light is constant.
Awesome. Why so?
I'm kind of obsessed with this right now, and just in general. But there's a long sort of backstory about like, because I'm trying to think about the principle of invariance, which is one of the things that Einstein like when he was developing the special theory of relativity, there were measurements that people had taken that many people didn't take seriously, that suggested the speed of light didn't depend on the direction and your motion relative to the light beam, right? So like it's constant independent reference frame. And that went really counter to like how people were thinking at the time. And so a lot of people thought the measurement was flawed, but Einstein did this thought experiment where he just accepted that the measurement was actually accurate. And he asked questions about what would be the consequences if this is accurate. And some of those consequences are things like the way he reasoned was to say that things that are laws of physics should be independent of the reference frame. So it shouldn't depend on the observer. It should be every observer would agree on this thing and this measured value. And that's a law of physics. And so he then was able to equate the speed of light with a law of physics. And the reason I think that the speed of light being constant blows my mind is because it does suggest that underlying all the subjectivity and all the other things that we've talked about in this conversation, there is an underlying objective invariant structure. And I think that underlying objective invariant structure is actually something that we're talking about when we talk about the causation and assembly theory, and there's some very deep relationships there that I'm exploring. But the fact that that exists and there's like all these other things that we layer on top because of the particular places that we exist as observers and how we're interacting with everything else, like that we would even have evidence of something being constant independent of how we measure it is it does something to my brain. that I like,
Yeah,
but I don't know what to do with it.
Yeah. I love it. Well, let's do some things for our audience's brains now. So we only have a few minutes left. I'm so sorry to our audience, but there's a lot of questions that are rolling in. But one of them, the first one comes from one of our old friends, Julia De Marinas. Julia wants to know, what is one misconception that people have about assembly theory that you'd like to write?
There's actually a lot of misconceptions, but I think some of the ones that we've been trying to tackle most is like, there's a lot of focus on the assembly index, the measure, like the mathematical measure and whether it's unique. And this first off, you can demonstrate it's not equivalent to other measures of complexity, but it's also weird to me that people would even ask that or fixate on that because it's kind of irrelevant to the whole conceptual infrastructure of the theory. It's not irrelevant. It's obviously an important mathematical component, but people confuse the map with the territory all the time. And like the way new theories emerge is that there's a set of concepts and you can look at like the history of physics, like they knew things before they could mathematically regularize them. Like there are patterns you understand and you just don't know the language to talk about them. And math becomes the language we talk about them and we can share it between us. And what assembly theory is doing is recognizing a set of patterns and anchoring that sort of set of structure that we think we need to understand in measurement. And the assembly index comes out of that process of trying to put the abstraction into the measurement and map it to the measurement. And that's why it has the structure it does. And that's connected to a whole bunch of other conceptual things in the theory. And it's not it's not decouplable. You can't replace it with another complexity measure. It's not even a complexity. We talk about it as a complexity measure because that's the language people have used to describe these things, but I wouldn't even call it a complexity measure. If I was going into it, I would say it's a measure of causation and selection in a physics that we haven't described yet, because it's really talking about how much causation and how much constraint does the universe have to pack in to generate this particular physical structure. And it's like, it has a different embodiment than these other things. But I think the thing that's hard with any new theory or idea is we have all of these sort of things we think about culturally, and we're trying to map them to things we know. And if somebody's trying to build a space of something we don't know, it's like that old meme about, touching the elephant. Are you actually seeing the elephant? So that's one that I think people talk about a lot. There's a lot of misconceptions because it's really hard to see the elephant that we're talking about. And I'm hoping that will come out in more papers. We have a lot of collaborators and everybody's working really hard on trying to describe these ideas that we've been working on in ways that are understandable and shareable so we can do more with them. That's a process.
Absolutely. And in this process of going from basic building blocks to larger ones, there's also minerals. There's a lot of abiotic structures that are formed. And so Hank Rainwater asked, what role you see for assembly theory in understanding transitions from like geology to geochemistry to prebiotic chemistry.
Yeah.
And how like there's different combinations, but then we have these larger structures that are forming.
Yeah. One of the things that's really tripping my brain right now is I think like when we do assembly theory for minerals and we do assembly theory for genomes, they're going to look really similar. And the physical structure of them in the theory is actually really similar because of the kind of like periodic lattice and aperiodic lattice, right? Like if you go all the way back to Schrodinger and what is life, he conjectured the genomic material was an aperiodic lattice to encode that much information. And if you look at the history of origin of life, it's like, Graham Cairns Smith proposed minerals were the first genes because they had a periodic structure that could encode information. So like we've been talking about these things for a while, but there's no common language to talk about them in the same mathematical structure. And I think it's crazy because as we're converging on building assembly theory for different kinds of materials. So far, the only published ones are covalent chemistry, but we're doing a lot to build it for proteins, genomes, minerals. And some of that structure is converging and has some commonalities that I think will allow us to see much more clearly the transition of information from minerals into covalent chemistry and the things that evolved as genomes. And right now, what I'm most interested in using assembly theory for is to figure out the system that built the translation machinery. So to go deeper than Luca and figure out what evolution happened before that. And I basically like a lot of my lab right now is working on this, but we're not working on it. Like we're working in that direction. Like this is where we're going. So I think like in 5 years, the one question I'm going to be asking is what constructor built the translation machinery? But yeah.
I love it. So we are getting close to the top of the hour. Do you have time for maybe one more question or two more questions?
I do. I'm sorry. I'm like giving long answers. I should give.
It's also my fault. I'm actually monitoring the clock a little closer.
Yeah.
It's so hard when we only have like 1 hour to get things in. So here's a question from Jessica Shumari. Jessica wants to know what sociocultural shifts you might expect as we learn more about the origin of life and emergence.
I think there's going to be a lot of them, but I think one of the things I'm kind of excited about, and I would like to encourage people like Thinking Astrobiology to do, is to look at what's happening in like really different fields, because there's a lot of like technical, rigorous progress happening. And what's interesting to me is if you look at the discussions around artificial intelligence, which I think a lot of them are deeply superficial, with related to like tech companies and sort of, the propaganda they're putting out there to like raise revenue for their interest in the fact that they have AGI when they don't. But, like they're like, if you look past the cultural narratives and that people are, trying to strategize, the way people think about things, there is a real discussion happening about, what does it mean to animate a machine? And I think there are a lot of parallels there that will become apparent to the way we talk about how do we animate chemical systems. And I think there will be some really interesting convergences there. And I just see this sort of knowledge that we're moving toward, if we solve the problem of what life is, as being transformative across multiple fields that we don't even know that this problem is really relevant to, far beyond that. Like there's material science, and drug discovery, and like real technical, rigorous areas where this can really impact. And I think trying to get ahead of it and look at those fields and say, how could my science really shift this, is incredibly fruitful for us as astrobiologists, because it gives us new horizons about what the impact of these problems will be.
Yeah. I love that so much. And that fits in with my own current work and this idea of the Panzoic effect, that thinking about alien life and our work in astrobiology also makes us want to be better people and think about our impacts in sociology, economics, politics, the way the world is changing and where we are right now in the history of the universe.
Yeah, it also might redefine what we mean when we say like we as people, right? Like individuals, and like the way we think about what it is to be human is also something that we've developed over time. And I think that will change.
Yeah. I love that so much, and as much as changing of what it means to be human.
It's exciting.
The future's still out there, though. I will say, so there's a bunch of other awesome questions from our audience. Thank you, everyone, for writing in. I think many of these questions could actually be answered if you read Sara's new book. I want to jump to my favorite one, though, the entire list I see in front of me. Marina R. on YouTube wants to know if you were to write your own science fiction book, what kind of idea or topic you might want to write about? So
I have thought about this actually, and I do have some aspirations to get in science fiction writing at some point, because I think some of the ideas, like one of the reasons I do all this work in the public facing like intellectual work is like when I'm out here, talking with you guys, like this is me actually doing the science, because I'm getting ideas from our conversation. And I think this is a much more collective process about how we come to new knowledge. And I think science fiction also plays a really big role in that. And there's some things that can be communicated through science fiction that just can't through the way we talk about things in science. So, which is the story, right? Like we can give a narrative of how we think reality works in science, but we can't give the story of the humans coming up with the narrative. And I guess that's the part that I would be interested in writing about. And I did start a science fiction short story at one point about the discovery of alien life. And maybe I'll finish it.
Cool.
Carl Sagan had contacts, and I think it really, it really framed the way he was thinking about the science. And so I did one about like thinking about these alien experiments and what it would really look like. But yeah, someday. There's not enough time for everything.
Time is so hard for all of us. We all want to do all the cool things, including I would love to have you on the show for way longer, but we are past the top of the hour, and I have to respect your time and our audience. So thank you for everyone who's watching, for tuning in live. For those who are watching the recording in the future from now, thank you for tuning in and being part of this with all of us. Sara, thank you so much for coming on the show and for your incredible book.
Thank you. Really fun to be back. It was great. And thanks for all the questions to the audience. That's great.
Yeah, hopefully we'll have you back next time in a shorter period of time, in less than 6 years. We'll see. But yeah, I would love to have you back on the show to talk more in the future. And once you write that science fiction book, I want to hear more about that as well. So thank you so much, Dr. Walker, for joining us. Thank you to our entire audience out there, everyone in the interwebs across the planet, and the aliens who might be watching sometime in the future our incredible show on YouTube for NASA Astrobiology and SegaNet.org. It's a pleasure to have all of you join us. So until next time, remember, stay curious.